mnemonic programming, and she's from Durham. Wow.
Yes, joint
Okay.
Actually, I'm going to keep one of these as a pointer. So, I'm going to talk from my elevator perch about computational thermodynamics. So slightly to one side of what everybody else has been talking about. But this is still very much in the flavour of physics and logic, because this is some work I've done with Samson. And we've basically taken a debate that's gone on for decades and decades in physics, and we've applied computer science methods to it, we've formalised it, and we've actually settled the debate in a way that, well, I won't say nobody can argue with, because we're talking about people in foundations, but in the terms of the debate as it was up until when we did this, we've settled it. So, what am I talking about? What's that?
Does John Norton agree?
I haven't asked him yet, but there really isn't any wiggle room, as you'll see. He has to invent something else to wiggle.
It'll be fun.
So what I'm talking about is a debate that Norton and Ladyman have been having around Maxwell's demon and Landau's hypothesis. So they've basically... Okay. Ice cream afterwards. So they've basically been looking at a very simple thermodynamic system and trying to see if they can prove Landau's hypothesis. So Landau's hypothesis, if anybody doesn't know that, is the one place where physics and information theory meet in terms of equations. It's sort of the one place that we have where information is physical really takes on a content, where if you erase one bit of information, it's saying you have to have a work cost of at least kt log 2. But it's an hypothesis. And if you look in half the textbooks, they say it's fact, which is rubbish. It's a hypothesis. And the problem has been people trying to prove it. And even in this really, really simple single particle in a box system, people have been having huge problems, and it's generated masses of paper. And what we've done is taken formal verification techniques from computer science, formalised that system, and then been able to prove that, first of all, the second law holds in that system under certain assumptions, and that Landau's hypothesis is correct in that system. And that system corresponds exactly to the one that Norton and Ladyman have been having their very, very publication-fruitful ding-dong about. So they will have to change their system to get around these results. But more importantly, what we've shown is that in really simple logical terms, how you have to have Landau's erasure. Because up until this point, nobody's really known where that's come from. There's been a few attempts to prove it, but generally with very, very complicated systems with huge numbers of particles. And we've done it with a single particle in the box. But first of all, I'm going to take 1 minute because I think Jamie, as I'm sure you're all aware, has given the world's best conference announcement when he moved my talk. So I'm going to just take a minute to explain what I was doing when I got my sword fighting injury, because yes, this is a sword fighting injury. That's the sort of thing I was doing. That's me. Only not actually that, because I was sword fighting on stage, ripped a calf muscle. The play's still on. Tonight and tomorrow night, Merton College, 7:30, you should all go to it, it's very good. So, back from Shakespeare to thermodynamics, I can't not start this talk then with "Oh, for a muse of fire." Only, as I said, I'm not dealing, like everybody else with Landau erasure, has dealt with these large thermodynamic systems, like large bits of fire. So instead, it's "Oh, for a muse of single particle gas in equilibrium with a heat bath at temperature T." Because this is the system I'm going to be dealing with. Like I said, it's very, very simple. So first of all, the thermodynamics of computation. Why do we think thermodynamics has got anything to do with computing? Well, it is Landauer and his information is physical principle. He was the first person to really connect together information and physics back in the 60s. But people have been talking about it before with things like reversible computation, because with thermodynamics you've got this one-way entropy-only increases. And if information is processed in physical systems, that's obviously going to have some impact on what and how you can process information. But what exactly is it? What's that connection? And like I said, Landauer's hypothesis that erasure requires a work cost was the only place where sort of the information level of description in terms of bits and the physics level of description, this time in terms of work and thermodynamic quantities, comes together. So what we're going to try and do is bring them further together. And to do that, we will formalise in the language of computation what's happening in the physical system. So I promised in my outline thermodynamics in one slide. This is it. Single particle equilibrium thermodynamics in one slide. All you need to know is that you've got a box and there's a partition that can come in and out. There are two pistons left and right that can come out. There is a single particle. And the pressure of that particle, as it bounces around, that's a thermodynamic variable, pressure P. There's the volume that it occupies. So there's either the volume of the total box or of half of it. That's the state variable. And then there's the entropy, and I realise I shouldn't have used this P. This P is the probability that's found on the left-hand side, and it's nothing to do with pressure. So that's your entropy, and we've basically coarse-grained the box, so there's two states. It can either be in the left or the right. And that's really it. You then have two equations of state, which is your PV over T is constant, and then that your entropy is equal. If you change the volume, then you change the entropy. That's it. That's all you need to know in terms of the physics. So now what we're going to do is take that physics and turn it into computer science. First of all, I'll say what the allowed operations are before we do that. So you can insert and remove the partition. That's an allowed operation. You can insert and remove the pistons to the left and right. And in fact, if you do that one that I just showed, that is known as isothermal compression. You're compressing the volume of the gas by a half, and by the equation by this equation, you need kT log 2 of work. So those are all the things that you can do with that system. It's really very simple, but even this really, really very simple system has generated so many decades of discussion, and people not being able to say whether or not every time you erase a bit of information in this, you have a work cost. So how do we formalise that system? How do we turn those allowed states and operations into something that looks like a programming language? It's actually very simple. I'm very aware this is an audience split between computer science people and physicists, and I'm trying to give this talk bilingually. I'm also aware of the time. So this probably to a physicist looks horrible, what I'm about to give, but it's actually really simple. Because this is where it's at really, the state variable. This contains all the information you need to know to construct the physics. So what is it? It's the probability that the particle's on the left-hand side, that's what big X is. And we're just taking the simplest possible distribution. It could either definitely be on the left, definitely on the right, or you don't know where it is. It's the only values we're allowing that to take. A and I are Booleans. Is there a partition? PA for partition. Is there a piston? PI? And this work counter is the total work extracted from the system, because its thermodynamics will be dealing with cycles. And it's in units of kT log 2, so it's just an integer. And you can convince yourself that that's all you need to know in order to reconstruct the physical state. because it's things like if there's a piston and it's definitely on the right, then obviously the piston is a left-hand piston because you can't put a piston through a particle because that doesn't work, because this is physics. So this is your thermodynamic state, but it's also the state variable within a logical structure of a programming language. So what we're doing is looking at the allowed transitions that you can give for state variables. So we've got functions on those and basic statements, and what we've done is take all of the allowed operations that you can give and write them in terms of functions that you can do on this. So this is the bit where physicists will probably want to close their eyes, because this is a syntax for what we're talking about. Again, it's very much simpler than you think it is. This is just defining all the things that I've been saying up until this point. That it's basically everything up to here is just to define what the state is, what I just said. This bottom one is to tell you what you can do with basic statements, basic transitions from one state to another. You can have sequential, probabilistic composition. We've got an if-then-else statement, and we've got assignment statements. It's really, really basic. It's based on the while language. There's nothing fancy going on in there.
Are you not distinguishing between your two pistons?
No, so like I said, it's the combination of the piston boolean and the position tells you which piston it is.
Okay.
So you don't actually need
Yep,
to
okay.
know. Yeah. That was one of the things that struck me right at the beginning, is I started off with listing all of the thermodynamic variables and realised the logical structure was so much smaller. And these are the operational semantics. This is formalising the operation, how you can describe the operations on the system. Again, much simpler than they look. We've got assignment statements, we've got how you can compose things, if-then statements, and probabilistic composition. This is all to enable us to write out programs that correspond to the allowed operations, which is what these are. So now it's using the semantics and the syntax to write out all of those operations I said right at the beginning we can do. So I'll just go through briefly these two. So this is inserting a partition. And I said S was your state variable. And this is an assignment statement. So it says what the function part in does is it assigns the Boolean true to the flag A, which was our partition flag. So basically, whatever you start out with, after you've inserted a partition, you have a partition. Hopefully that's obvious. Removing a partition, slightly, we've got to get some if-then-else statements in here. Because unlike when you're debating about these things in sort of foundations of physics, to write this out as a programming language, you have to cover all bases. You have to be able to apply this function to every state that's physically possible. Even ones that you normally wouldn't. Like, remove a partition. Well, we've got to have the else skip, which is if there isn't a partition there, it says you don't do anything. So this is, if there is a partition, so if the partition flag is true, then if there isn't also a piston, then the particle becomes completely delocalized. You don't know whether it's left or right. And the partition flag goes to false. And if there is a partition, if there is a piston, then it doesn't delocalize because the piston keeps it there, and the partition flag goes to false. And if there wasn't a partition, then we don't do anything. So that's a way of reading this language. These are the other operations. I'm not going to go through them in great detail, apart from to say here, this is removing a piston to the left. And we now get some, if you like, thermodynamics coming in, because this last line is isothermal expansion. If you don't have a partition there, then the gas is actually doing, the single particle is doing work on the piston, pushes it out, so you iterate the work counter by 1. And the same out to the right. Inserting a piston is actually much more complicated, and it took us ages to get this one right. So can you insert a piston to the right here? Yes, no, no. I've got it right there. I had the transitions on the keynote. Yeah, because otherwise you'd be compressing to zero volume as well as all of this stuff. That's called an explosion. So what do? Normally in the literature you never try and do this because you're writing debates going, well, obviously you would never try and compress to zero volume. You'd only insert a right piston if there wasn't the particle on the right. But because we're programming, we have to, as I said before, cover all bases. And that's where it gets interesting. Because if you consider this cycle, which is you start out with the thing completely delocalized, but there's a partition. You don't know if it's left or right. We'll start with it completely delocalized, put the partition in, try and put a left partition in, left piston in, sorry. Take the partition out, and then take the left piston out. Now, if it's on the left, then when you try and put the left partition in, you're trying to do an illegal operation. If it's on the right, however, you've inserted a piston, and then when you take the partition out, the gas then does work. So half the time you're getting work for free. The other half the time you're trying to do this illegal operation. So the expected work extracted from the system is this here. And it's returning to the same configuration at the end. So you could just repeat this over and over and over again. And if there were no penalty to trying to do this illegal operation, you would have a perpetual motion machine. It would just produce work. Because half the time, it would give you work for free. So there has to be a work cost to trying to compress to zero volume. It's nothing to do with, we've not formalized the second law. It's just saying no perpetual motion, no energy for free. We have this work cost, and it's got to be greater than equal to 1. We set it equal to 1. Therefore, we have probabilistic operations. Because if you don't know where the particle is, if you try and insert a piston, half the time, you guessed correctly, you insert the piston, and half the time, it kind of bounces back out again and you incur this work cost. So this plus is telling you that half the time this happens and half the time that happens. So we've got a probabilistic dynamical system. Just to see this for a little later on, we've got two types of probability going on. So we've got this probabilistic composition, and we've got the original probability in the fact that you can have your probability being on the left-hand side is a half. So two types of probability. So what can we do now that we've got all of this formalized? We've got programs and subroutines for all of our allowed transitions. We can do something called finding a probabilistic computational invariant. And this is the point where Sampson starts talking about Clazy extensions of the monad, distributional monad, and I go, hang on, you're just talking about expected values of probability distributions. That's all that's going on. So for a physicist, this is really, really straightforward. And it's this thing that for computer scientists, it goes on forever. But basically an invariant statement is a predicate. It's not a quantity, it's a predicate that if it's true before a transition, is true after it, and it's true under composition. So basically what we want to find is an invariant statement for all of those allowed operations, so that you can say if the invariant statement is true beforehand, then any combination of those allowed operations under the sequential and probabilistic composition laws that we've got also makes the predicate true afterwards. What's the invariant statement? I want a drum roll here. And if anybody recognises it, tell me. Because it's not just the entropy. This statement here is the computational invariant of this system. I just rolled T into the entropy. And I'll talk some more in another slide about exactly what these are. So the angle brackets is the expected value over the branches of the computation, over the probabilistic branches. So what we would expect, if you're a physicist, you would expect the work would be balanced by the entropy, and they would be less than or equal to 0. But it's not the entropy. It's not the standard h of x that we would expect. I tried that. It doesn't work. It took forever to find this one. So if anybody recognises this quantity, if you put a minus sign here, it's the Halevo quantity. But that one I've not seen. But basically it says this entropic quantity must always be balanced. If that changes, if it increases, then it must be balanced by an increase in the work, averaged across the branches of the computation. But every composition of those simple transitions, if it satisfies this beforehand, it must satisfy it afterwards. So, first off, let's look at the second law. Kelvin's statement of the second law: you can't return to same configuration having extracted work from the system. So that says that your x, which is the equivalent of the configuration here, that's the variable that tells you the configuration. You can't return to the same x with your partition and piston flags the same and having extracted, on average, a greater amount of work than was there at the beginning. So if we define always the 0 point of the work counter whenever we're looking at cycles as this quantity, that satisfies the invariant with equality. This thing is just a counter. It doesn't matter where the 0 was. That's nothing to do with physical situation. So we can set it to what we like as long as we keep it there. So set it there. Then the final invariant, if we return to the same x, is this thing here. And because we know that this was equal to 0 with W naught here, it straightforwardly implies that you cannot have an average quantity of work extracted from the system that is greater than your initial work count. That's the second law. And that comes straight from the invariant. So we have proved that this basic system, under those allowed transitions, satisfies the second law in its Kelvin statement. No argument. We can go one better. Landau erasure. What does Landau erasure look like in this? So there's two entropies in this invariant quantity. So this, the average entropy, you can think of that like you've got an entropy in each branch of the computation, because x is either 0, 1, or half in each branch. Average that across the branches, you get this entropy. This one is the entropy of the probability distribution. You can think of them like entropies horizontally and vertically. If you have an unknown state that there's a partition in, so it's either left or right, you don't know which one it is, then both entropic quantities are k log 2. If you measure one of them, then you've still got two branches. You've now got two branches in your computation. Before you just had one, x was a half. And in one branch it's definitely left, and in one branch it's definitely right. So the entropy in each branch is 0, and so the average entropy per branch is 0. But the entropy of the probability distribution is still k log 2, because there's two branches. So that's what measurement does. A reset to a known result, say resetting it into the left-hand state, takes you from two branches to one, and you know where it is, it's x equals 0 here. So a reset takes the second entropic quantity also to 0. So we've got these two ways that you can manipulate the entropies. Given this invariant, we can say the cost of doing these. Because this invariant tells us the work cost for setting this to 0 and setting this to 0. If you have a bit, then sending this entropic quantity to 0 requires at least a half kT log 2 of work. if you have a bit, you've measured it and then you reset it, you're sending this entropic quantity to 0, which also requires at least a half kT log 2. So if you have an erasure operation, a measure and reset, this is something I don't have time to go into in detail, but measure and reset, you have a particle, you don't know where it is, you measure it, you reset to a known state. That requires a work cost of setting this to 0 and this to 0, both of them added together, kT log 2. That is Landau erasure. So in this system, it is a logical consequence of this system that when you measure and reset an unknown bit of information, you have to have a work cost of at least kT log 2. And conclusions, we've proved Landau erasure in this system. It's awesome. There's lots of further work. I'll finish.
Questions, comments?
Possibly a dim-witted question. Now that you've identified the computational invariant, would it be possible for you to go back and rewrite the entire argument without reference to the programming language and its formal semantics and so on, simply as a proof in the style that would say, here are the operations, and here's the invariant that one has as it applies these different.
So not into, if the, it depends, do you mean do it as a physics argument rather than a computer science?
Mathematical physics argument. Yes.
Okay, so that's, so here, what's the relationship to the second law? That's basically where this further work is going, which is taking that as is that a statement of the second law, basically? Can we reverse engineer a law of physics from that invariant? Because it ought to be. But there's things like these two different types of probabilities going on, which has an interesting connection to quantum, which I haven't had time to go into at all. But yes, trying to then step back into physics is the next step.
Okay, we thank Claire again.